Bismillahirrahmanirrahim. Assalamualaikum and a very good morning. Okay, radiation mechanism. So electromagnetic radiation is produced by the changing of time-varying electric and magnetic fields due to the acceleration or deceleration of charges Q. Okay, if you have a charge, if it is static, so there's no current or time-varying current produced, therefore no radiation. But if the charge keep on moving forward, backward, and so on, okay, there's time varying electric and magnetic field produced, therefore the electromagnetic radiation or EM wave exists. Okay, by referring to these figures, okay, the figure basically representing different types of radiation depending on the structure, a different type of structure. Okay, so for example, the first one, for straight wire, okay, if there's charge but the charge is not moving, so there's no current or time varying electric and magnetic field, therefore no radiation. However, for the same structure, straight wire, if there's charge moving but with uniform velocity, still there's no radiation if the wire is still in straight condition. However, if the same wire is then bent or truncated and the charge is moving with uniform velocity, there's radiation exists. And lastly, okay, if there's charge oscillating in time motion, okay, oscillation, so radiation exists although the wire is straight. Okay, there's no specific rules for selecting an antenna for any particular frequency range or application. Okay, but the antenna is designed based on the intended application. Okay, for example, the antenna, the system needs a narrow bandwidth, very high efficiency, broad beam width, and so on. Okay, the slide shows the antenna parameters from the circuit design process up to the transmission state. Okay, so in this course, we are going to discuss the space quantities, okay, related to the radiation pattern, polarization, directivity, gain, and etc. Okay, the first antenna parameter that we are going to discuss is the radiation pattern. So the radiation pattern is basically the representation of the radiation properties of the antenna as a function of space. Okay, this is the graphical representation of the antenna radiation pattern, in which we may see the maximum radiation towards the intended direction. Okay, in this case, the maximum radiation presented by the red color pointing upward. Okay, and there are additional components in the radiation pattern, which are the side lobes or minor lobes, and also the back lobe. So the radiation pattern may be presented in 3D. So this is the example of 3D radiation pattern, or in 2D patterns. Okay, in 2D patterns, either it is in polar form or Cartesian form. And the plot, 3D or 2D plots, may be presented for both horizontal and vertical plane or representation. Okay, okay, this is an example of the 2D radiation pattern. So the components that can be measured from the radiation patterns are the 3D beam width, Okay, for example, this is the beam width, and then the directivity, so the intended direction, whether it's pointing to the front at 0 degree or at elevation angle of 30 degree, and etc. And then we can have the side lobe labels as well, front to back ratio, and others. Okay, if an antenna acts as a transmitter or receiver, okay, the radiation pattern will be similar, okay, due to reciprocal characteristic of the antenna. Okay, for example, if it is a transmitter, so this is the radiation pattern, or if it is acting as a receiver, and it will be having the same radiation pattern. Okay, these are the basic definition of field pattern versus the power pattern, either it is in linear scale or in dB. Okay, for field pattern in linear scale, it represents a plot of the magnitude of the electric or magnetic field as function of space. Okay, for power pattern, either it is in linear or in dB scale, represents a plot of square of the magnitude of electric or magnetic field as a function of angular space. Okay, so if this is in dB, so the square of magnitude will be in dB as well. Okay, as mentioned in the slides number 6, the radiation pattern is determined in the far field region. So where is the far field region? If we refer to this figure, you may see that the far field region is the outer layer of the region from the antenna itself. Okay, so the R is basically the distance from the antenna. So the far field region appear when the distance from the antenna is larger than 2d squared over lambda. Okay, when a signal is fed into an antenna, okay, the electromagnetic wave will be sent out over the free space, and the electromagnetic wave may be characterized by a function of distance from the antenna. So we may see that the EM wave behave differently when the distance between the antenna is varied. Okay, and antennas usually used to transfer signal at large distance, which are considered to be in the far field region. Okay, so this is the region of operation for most of antennas. Okay, in measuring the antenna in far field region, we have to make sure that the R, the distance from the antenna, okay, the distance from the antenna must always larger than D. D is the overall dimension, overall linear dimension of the antenna, and the R must always be larger than the lambda as well. So lambda is the wavelength of the antenna at the intended frequency. Okay, so in this case, in the far field region, so R2 must be larger than 2d squared over lambda. So d is the linear dimension of the antenna, and lambda is c over f. F is the frequency, the resonant frequency, or the intended frequency of the antenna. Okay, this slide shows some 3D representation of the radiation pattern. Okay, next is the 2D radiation pattern. It is basically the extraction or the cut off from the 3D pattern at some plane. Okay, for example, if we cut it somewhere here, okay, and we look at from the top, we may see this shape from top. Okay, we cut this at this plane, and this plane is called horizontal plane or azimuth plane. okay, also called horizontal plane or H-plane, horizontal. And on the other hand, when we cut it over here, we cut it half over here, so we may see something like this, something like figure 8. Okay, this is the figure 8 shape when we cut it vertically or at elevation plane. Okay, so the antenna the radiation pattern may be presented in 2D plane. Either it is in polar plot or in Cartesian plot of coordinates. Okay, this is, for example, from this donut shape. When we cut it in vertically, okay, we may see figure 8 shape from the antenna pattern. And when we cut it horizontally or H-plane or azimuth plane, we may see a round shape of the antenna pattern. Okay, let's look at the example of the radiation pattern for the dipole antenna. So this is dipole antenna. So for 3D radiation pattern, it looks like the donut shape. So when for the azimuth plane, the H-plane, okay, when we cut it here, okay, and we look from the top, we may see a round shape, okay, represented in the H-plane, while when we cut it vertically, okay, half of it here in this plane, in the E-plane, so we may see the donut shape in the E-plane or elevation or vertical plane. So for this shape of antenna or radiation pattern, so again, when we cut it horizontally, we may see again another round shape or omnidirectional pattern. Omnidirectional meaning the radiation across all direction. Okay, but when we cut it vertically here, okay, we may see there's something like small loop there, and there's another small loop at the bottom, and we can see the other two front loop and back loop. Okay, so we can see something like this in the E plane. Okay, this slide briefly defined what is E plane and also what is H plane. So E plane is the elevation or vertical plane in which contain the electric field vector and the direction of maximum radiation, while the H-plane or horizontal plane, or also called azimuth plane, is defined as the plane containing the magnetic field vector and the direction of the maximum radiation. Okay, so this is the horizontal plane, H-plane or azimuth. This is the 3D pattern. So when it is cut at azimuth plane or horizontally, you may see a round shape or omnidirectional pattern. If you cut it vertically, so you may see figure 8 in vertical plane, or also called elevation or E plane. Okay, another term that may be useful in antenna design is normalized radiation pattern, in which the pattern shown being normalized to the peak gain. So when you look at the maximum radiation, it is 1 because it's already being normalized to the peak gain. And normalized pattern is especially useful when the side lobes level and the depth of the null. So this is the null area. When the depth of the null and the side lobe levels are of interest and it will be much easier to analyze or to read through the pattern and all levels. All right, so this is from the 3D pattern. Okay, these are the major loop area. And then we have the half power bandwidth, HPBW, okay, in which it happened at -3 dB when the power has been reduced by 50% from the peak power, or it is basically 0.7 or 7 in voltage. Okay, and you may see the minor loops and side loops here, and the back loop is basically the opposite from the major loop. Okay, the radiation pattern will determine the characteristic of the antenna. Okay, some application may require very little or no side loop, no back loop. Okay, because for example in human health monitoring, so the antenna should be designed with lower back loop, okay, to make sure there's no energy being absorbed by the human body. Okay, these are some representation of the normalized radiation pattern in linear value and also in dB values. Okay, next is the radiation pattern loops. As mentioned earlier, it consists of the major loop where it has the maximum radiation in the intended region, and it consists of full null beam width. Okay, so we can see that at this point it put the magnitude is 0. So when we represent it in 2D, so this area, this one is the region of full null beam width, while the half power beam width is from this area to this area in the plot. So again, half power bandwidth represented by -3 dB when the power is reduced by 50% from its maximum value, and the side loops can be seen on the right and on the left hand side. Okay, loops, by definition, it is various part of the radiation pattern, consists of main, minor, side, and back loops. And the radiation loop is the portion of the radiation pattern bounded by regions of relatively weak radiation intensity. So the side loops represents the weak radiation intensity if compared to the major loop. So major loop also called main beam, which defined as the radiation loop containing the direction of maximum radiation. And then the side loop is a radiation loop in any direction other than the intended loop or the major loop. And the back loop is the radiation loop whose axis met an angle approximately 180 degrees with respect to the main loop or the main beam. So it's basically, the back loop is basically opposite the major loop. Okay, next is the pattern classification. It depends on the direction of the antenna. Okay, this is for isotropic or omnidirectional pattern in which the antenna radiates equally in all directions. Okay, for example, if you have a dipole antenna, okay, you may see the radiation pattern is in circular shape or donut shape. In this representation, we may see the maximum radiation represented by red color. So the maximum radiation occurs surrounding the structure. Okay, so example, dipole antenna emit equal power in all horizontal direction. and this is also called omnidirectional pattern. So when we plot it in 3D or 2D, it looks like a donut shape. Okay, another types of pattern classification is directional pattern. By definition, directional meaning that the antenna radiating or receiving electromagnetic wave more effectively in some direction than the other directions. For example, the horn antennas, okay, having the main lobe pointing upwards. So this is showing that the horn antenna having the directional pattern pointing to the intended direction. Same goes to the Yagi-Uda antenna, also having the directional pattern in which we can see the main lobe pointing upwards while having the very minimal side lobes and also back lobe. Okay, another parameter can be measured from the radiation pattern is the beam width. So the beam width is the angular separation between two identical points on opposite side of the pattern maximum. So there are two types of beam width, which are the half power beam width, HPBW. This happens when the power reduced by 50% from the maximum power. It is at -3 dB level. And the first null beam width is the angular separation between the first nulls of pattern. Okay, so this is the first null of the pattern. So where the FNBW is measured, and the HPBW, the half power beam width, is measured at -3 dB or equal to 0.707 in linear. Okay, from the description of field pattern and power pattern in slides number 7, and this figure, you have seen this in slide number 12. So let's look at the difference between these figures. Okay, this is the field pattern in linear, in which it is the normalized value. Same goes to the power pattern, normalized value in linear scale, and this is in dB scale for power pattern. Okay, for field pattern in linear, the maximum radiation is 1, and the HPBW half power in dB is -3 dB. Okay, so in which for power pattern in dB, you may see the power reduction by 3 dB at 3 dB point, in which the power has been reduced by 50%. Okay, and in linear, this 3 dB for field pattern equal to 0.707. So the HPBW is the separation difference between on the major lobe. So this is your major lobe. Okay. So this is your major lobe. So the separation, the angular separation distance between two half power points. Okay, so half power point in this case in field pattern linear is at 0.707. So this is your HPBW between 2 points on the major lobe. So the HPBW is the angle between these 2 points. So it's the angle between these 2 points. Okay, so the theta is measured from this point up to this point. So this is theta. So meaning that HPBW will be 2 theta. For field pattern, the reference power is 0.707 in linear. But for power pattern, okay, the maximum power is 1 in linear, and the half power in power pattern equal to 0.5. Okay, this is for power pattern, and the first one just now is field pattern in linear, both in linear. So for power pattern, the half power is equal to 0.5. So H half power equal to 0.5. For field pattern, the half power equal to 0.707. So at this point, the same concept is the angular separation distance between two half power points. So for this power pattern, half power point is at 0.5. Okay, so the theta is in between here. So this is your theta, meaning that for power pattern, the theta equal to, so again the theta is measured on the right hand side for theta, meaning that HPPW equal to 2 theta. So considering both sides. Okay, for power pattern in dB, so as mentioned earlier, it is the half power points is 3 dB down from the maximum radiation, intended radiation. Okay, so the theta, the HPPW for the power pattern in dB again equal to 2 theta, and it is happening at minus 3 dB points. Okay, it's very important to read through the condition whether you are having the power pattern or field pattern in your analysis. Okay, let's look at this example. An antenna has a field pattern. Okay, so the keyword here is field pattern given by this equation. Find the HPBW. Okay, and it will be in radians or degrees. Okay, if it is not stated whether it's radian or degrees, you may calculate either one. If stated both radians and degrees, so you need to convert the radian into degrees as well. Right, so field pattern. Okay, so considering the main lobe, we know that this is the theta, and the maximum radiation is 1. So for field pattern, the 3 dB point is at 0.707. Oops. At this point and this point, it's 0.707. So you need to calculate the theta in between this separation. This is equal to 2 theta. Okay, so you are given the field pattern equation, E theta equal to cos theta, and the half power beamwidth for field pattern linear is equal to 0.707. So you need to calculate the theta. Okay, so by using identities, okay, so you need to consider some mathematical operation here. So for cos squared theta equal to 1/2 1 plus cos 2 theta, it is equal to the half power 0.707. So your cos 2 theta equal to 0.707 multiplied by 2 minus 1. So you can calculate your 2 theta equal to 65.5 degrees. Okay, so meaning that your HPPW, so therefore your HPPW is equal to 65.5 degrees, or if you want to use radians, so you can convert this into radians, and if not, then you can just leave it as the degree value. Okay, since the question asks you for HPPW, so you need to consider both the 2 theta. If the question only asks you for theta, then you need to divide this equation, the theta, by 2. Okay, let's look at the second example. Given the following condition, so the question asks you to find the half power beam width and also the first null beam width in radian and degrees for the following radiation intensity. Okay, what is radiation intensity? It's basically the power. Okay, in example 1 we use the field pattern. So in this case the radiation intensity presented by the power pattern. So we know half power for power pattern equal in linear equal to 0.5, and the null power, okay, since it is null, so it is equal to 0. So this is the power pattern. So we're still considering the main lobe. So maximum is 1. And then we have the half power at 0.5. So you need to measure the theta in between 2 points. So this is your HPBW, which is equal to 2 theta. Okay, and then the null power is measured at the null position. So this is null position near the major loop. So this is your null pattern separation, angular separation. So at 0. So you need to find we can call it, this is theta HPPW, and this is 2 theta for the null, the n. Okay, so let's consider the given equation. So the radiation intensity U theta equal to cos 3 theta. So for HPPW, we know that this cos 3 theta equal to the half power is 0.5. So you need to find the theta. So in this case, 3 theta equal to inverse cos of 0.5, which is equal to 60 degree, and the theta equivalent to 60 divided by 3 equal to 20 degree. Okay, but don't forget that HPPW, you need to find it, the separation and the angular separation given by 2 theta. So 2 theta for HPPW equal to 2 times 20 degree equal to 40 degree. And don't forget that the question asks you to provide the answer in radian as well. So you need to convert these 2 theta in degree into radian. So in this case, in radian, it is equal to, so 2 theta h equal to 40 divided by 180 times pi, so you get 2 pi over 9 radians. So your HPBW equal to this. Okay, and next you need to get the FNBW, the first null beam width, again in radians and degrees as well, so the same steps, but the power now equal to 0. So for FNBW, so you have the same equation, so cos 3 theta equal to 0. So calculate the theta. It's supposed to be 30 degree. Okay, let me calculate. Inverse cos divided by 3 is 30 degree. Okay, don't forget for F and BW, you need the 2 theta, and for now, so this is equal to 2 times 30 equal to 60 degree. And don't forget to convert that into radian as well. So in radian, 2 theta null equal to 60 divided by 180 times pi equal to 1 over 3 pi. Don't forget the unit in radian. So therefore, your F and BW equal to 60 degree, also equal to 1 over 3 pi radian. Okay, with that, I'll end this session. Thank you.
Thank you.